Hi there. Thanks for joining us. This is a Q&A episode of Space Nuts. That's me. That means there's questions that people ask and there are answers that I do not give. Someone else will do that. But coming up, we're going to get to something we planned to do last week, but it was a big question which required a lot of effort and a lot of answers and a lot of research. We just sort of ran out of time. So we'll get that one done today from Fenton. Kerry is asking about the effects of light by dust clouds or the effects on light. Nigel is talking brown dwarfs, and Paddy, Marsquakes. That's all coming up in this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining us again is Professor Jonty Horner, who is a professor of astrophysics at the University of Southern Queensland, a horrible part of the world, but somebody's got to live there, haven't they, Jonty?
Absolutely. It's a tragedy. It's glorious here at the minute, but we could do with a bit of rain. That said, given the amount of rain that's happening elsewhere in Australia, I'm probably glad that we're not getting that.
Yes, much, much further north than you are, up around North Queensland, Townsville area. It's been bucketing down and they've had some big floods.
I'm trying to get my head around the concept of getting 2 meters of rain in a couple of days.
Yeah, I can't. Yeah. A big rain for us is 80 millimeters in an hour.
Yeah.
That's a big rain. I think the biggest I've ever experienced here was 200 millimeters over a weekend.
Yeah,
that was some years ago, and that caused big floods across the area. But the numbers they're talking up there are astronomical, and our thoughts go out to everybody affected.
Oh, yeah.
Now, we should get straight into Fenton's question because it's a big one, and we'll be back in about 2 or 3 hours once he's finished.
Hey, Fernando, this is Fenton, speaking to you from St. Paul, Minnesota, in the U.S. on the other side of the planet. I got some questions for you today about radiation. Now, right now, we have spacecraft that are underway to Jupiter, and there's a lot of fretting about what's going to happen and how to get them to avoid radiation blasting off of Jupiter. So we have 3 types of radiation, alpha, beta, and gamma. If you wish, I'll leave that up to you to explain that to the audience. My question to you here is, what type of radiation is that's coming off of Jupiter? Is it just the alpha particles? In other words, just protons, hydrogen atoms? Now, here we go on to Io. Now, Io is also blasting off particles from its surface as a result of it being volcanic. So I guess that means we have these charged particles coming off. Do you want to also include them in the term of radiation? Now, I was also interested in what types of particles they have. These are metals, apparently. For example, if it were iron, and if it were charged, then iron can be magnetic. And that means it could possibly be interacting with the magnetic field of Jupiter. So where's that stuff going? Is it sticking around Jupiter? Is it heading off beyond Jupiter? Is it landing on some moons? And lastly, I want to ask you about a practical application for this. Now, here back on Earth, we can deposit metal ions from the gas phase onto substrates, and that has a lot of very useful applications. It's pretty expensive, too. So what happens if we put a substrate in the way, in blocking those metal ions or metal particles that are coming off of Io? Could we use that to deposit metals onto a surface? Just a thought. I'd love to hear what you think about it and where you take my questions. Have a great week. Bye now.
Thank you, Fenton. Always thinking deeply is Fenton. His questions are always multifaceted, and that one is no exception. So he started off talking about the different types of radiation and which kind is it's coming off Jupiter.
Yeah, I'll dive through this step by step, but what I will do initially is, it's a fabulous question. There's a lot in here. Yeah. I'll recommend for the interested listener who wants to dig into Jupiter's environment a little bit more, there's a Wikipedia article about Jupiter's magnetosphere, which is literally magnetosphere of Jupiter, which is incredibly thorough and detailed and goes into some of the things we're about to discuss in more detail than I will do. Now, Wikipedia is a fluid resource. It can be changed, so your experience may vary. But what we typically see is for astronomy and space subjects, they are not controversial, but there's enough people out there who are incredibly passionate about it that when an error creeps in, it gets fixed very quickly. So whilst it's not the most reliable resource, it can be very, very good. So I do recommend looking into that if you want more details on some of the stuff we'll discuss. But I'll try and pick through the many things Fenton said there in turn, just to try and work through them, if that makes sense. And hopefully that'll be helpful, Fenton, if you're listening in. Firstly, when you mention 3 types of radiation, you're talking there about alpha, beta, and gamma, which are the kinds of radiation that people talk about being produced by radioactive decay. And there are 3 kinds of radiation, but they're not the entirety of what radiation is. And they're actually different kinds of thing anyway. So alpha radiation is essentially helium nuclei. So 2 protons and 2 neutrons stuck together, coming outwards. That's a fairly substantial particle. So that's radiation as a particle. It's a particle that's ejected, in this case, from a radioactive process, flung outwards with a certain speed, and it's carrying energy from one place to another in the form of the particle itself moving at that speed from A to B. Beta radiation is electrons, essentially, so much less massive, typically traveling much faster, that are again produced by radioactive decay quite often in other processes. Alpha particles are positively charged because they've got protons in, but no electrons. Beta radiation is negatively charged because it's got electrons in. And then gamma radiation is very high energy electromagnetic radiation. So that's the top end of the electromagnetic spectrum, which also features light that I'm using to look at Andrew while I waffle away here and see him nodding unwisely. So they're different bits of radiation. Essentially, at the very simplest end, you talk about radiation just being energy being moved from one place to another, and that can be done by waves or particles. So at a very extreme stretch, you could probably argue that when you go outside and you turn the hose pipe on and you have a jet and that water is going from one place to another, that's a form of radiation. It's energy being moved from one place to another. So there's a lot of different ways that energy can be transferred in this way. And light in its many forms is one of them. So that's everything from gamma rays at the high energy end to radio waves at the low energy end, with optical and microwave and infrared in the middle somewhere. So there's a lot to radiation there. Now, there's a couple of things happening with Jupiter. Firstly, you talk about the radiation coming off Jupiter. Now, if you think about Jupiter, the planet itself, it's sometimes said that Jupiter emits more energy than it receives from the sun. And that's a leftover from Jupiter's formation, from all the material coming into it, the gravitational relaxation of it, essentially. That is energy emitted in the form of electromagnetic radiation. So light, essentially, of various wavelengths. It will emit as what we call a black body, so it'll have one particular color of light that it emits out most strongly. And whether you go bluer or redder of that color, it will emit more weakly as you go further away. So that's Jupiter emitting energy, but it's also surrounded by an incredibly intense magnetic field, much stronger than the Earth's. So hop to the Earth briefly. One of the challenges that people face when they fly satellites around the Earth is that there are these radiation belts around the Earth called the Van Allen belts. And they were proposed just prior to the space age and then detected by the first satellites. What's going on there is that the Earth has a magnetic field around it that interacts with the magnetic field of the sun and the rest of the solar system. And we've got this area around the Earth called the magnetosphere. And the magnetosphere is sculpted and shaped by what's going on elsewhere. Now, in the case of the Earth, you've got solar radiation in the form of charged particles as part of the solar wind, buffeting against our magnetosphere, penetrating in. And when you have particles that have charge, whether they're positively or negatively charged, they interact with magnetic fields. So they will follow the direction of the magnetic field lines. And our magnetosphere shields us from a lot of the radiation like that because it goes around the Earth rather than hitting us. But some of the radiation in the form of charged particles that penetrates the Earth's magnetic field then gets trapped in the magnetic field in these belts that we call the Van Allen belts, which are areas where you have a lot of charged particles moving around at high speed, trapped in these belts around the Earth, between a few hundred and a few tens of thousands of kilometers above the Earth's surface. Those are areas where if you fly a spacecraft through there, there's a lot of charged particles crashing into your spacecraft at high speed, that can damage the electronics. The circuitry in particular is very sensitive to this, and gradually damage your spacecraft and take it out of operation. So that's the radiation environment around the Earth, and they try and avoid going through the Van Allen belts as a result. Jupiter's the same. Jupiter has a much more intense magnetic field, so it can have a much more significant area of radiation belts. And those radiation belts correspond roughly with the location of the large moons, particularly Europa and Io. So in that area, when you're a spacecraft moving through there, you're moving through a soup of high-speed charged particles that are continually bombarding your spacecraft, degrading it, damaging it. And of course, they're particularly damaging to the electrical componentry. So you want to spend as little time as you can there. And that's essentially what the concern is for the scientists who are sending spacecraft to Jupiter. So that's what's going on there. Added to that, though, you've got the volcanism from Io, which Fenton mentions. And Fenton's quite right. Io is erupting continuously volcanically into that radiation environment around Jupiter, adding, I think some quotes say, up to 1,000 kilos per second of new material into that environment. Now, the atoms that are launched out of Io by this volcanism are things like sulfur, oxygen, sulfur dioxide, all these kind of things that initially are molecules and atoms, but are very quickly ionized. So they have an electron knocked off, colliding with these charged particles, which suddenly means you've got sulfur ions, oxygen ions, sodium ions, all floating around in the magnetic field. So Io is dumping even more charged particles into that radiation belt. Those charged particles from Io, incidentally, flow along Jupiter's magnetic field lines and crash into the Jovian poles, creating hotspots of aurora. So there are aurora on Jupiter that are directly linked to Io and, to a lesser extent, Europa and Ganymede. You can see them if you look at aurora maps of Jupiter that our spacecraft has sent back. So you get this flux torus connecting Io to the poles of Jupiter, which is the charged particles flowing along the magnetic field lines and crashing into Jupiter's poles. So that's how Io's chipping in. It's just adding more soup to the mix, essentially. Moving on to the metals being magnetic. I've tried to get through all the points.
Yeah, I just thought it was fascinating that there's such an effect happening around Jupiter, unlike like we see similar effects with the Aurora Borealis and the Aurora Australis, but different reasons, same effect.
So you'll have aurora on Jupiter that would cause the same way as the aurora on Earth, but you also have Io, Europa, and Ganymede cooking their own aurora as well. So it's complicated, I think.
Yeah, sure it is.
With the metals being magnetic, there's a couple of things there to mention. You're entirely right that metals like iron and nickel can become permanently magnetized, and this is something called ferromagnetism. Now, I'm not a specialist on magnetism by any means, and one of the common jokes in astronomy is if you want to ask a question at a conference, it's almost certainly, have you considered magnetic fields? And the answer is almost certainly no, because it's just complicated. There's actually a few types of magnetism that involves physical materials out there. Ferromagnetism is the most famous because it's the one that's easiest to observe with magnets. But that kind of interaction with magnetic fields is not what we're talking about here. So we're not talking about solid lumps of a metal interacting with a magnetic field. We're talking about individual atoms and molecules that have been ionized. And they're interacting with a magnetic field not because they are magnetic, but because they're electrically charged. And it is a subtle difference, but it's worth flagging out that there are two different things there. Now, the practical application you talk about having something there for all this stuff to smack into, is exactly what they're doing. So if you've got your spacecraft with all this valuable electronics on it, you want it to live as long as possible at Jupiter, so it costs a lot to get there. And they're doing two things simultaneously to maximize the lifetime of these missions. The first adds weight and therefore adds cost, but essentially for Europa Clipper, the entire instrument suite and everything that does the science that they can protect is enclosed in this hard shell, which is made of about 100 kilograms of titanium. So titanium, very dense, is like a protective shield around it. I guess serving much the same role that your windscreen does when you're driving through a rainstorm. The water hits your windscreen rather than hitting you in the face. Same kind of idea. So that's part of how they're solving it, which is exactly what Fenton was talking about with having the ions and stuff splat into something and coating them, essentially. The other thing they do is linked to bandwidth, and this is a perennial issue in Australia with the quality of the national broadband network and with things like Starlink. You want as much bandwidth as you can to transmit data around. And the bandwidth you get back from Jupiter is pretty low because you're so far away. Basically, the further away you're broadcasting from, the lower your bandwidth is. And it turns out that we don't have broadcasting equipment on these satellites, on these spacecraft, strong enough to send back the data in real time. The rate at which you get data is much higher than the rate at which you can send it home. So what that means is if you went into orbit around Europa, you would be gathering data much more quickly than you can send it back. And then when your spacecraft dies, you've lost all of your data. So you want to maximize the amount of time you can spend gathering data that we get back. And the way they've solved that partially is by having the cladding, the protection, that titanium cell. But that's why they've opted to, instead of orbiting Europa, to move on a highly elongated orbit around Jupiter and have flybys. Because the amount of data they can gather in a 1 hour flyby might take them several days or a week to broadcast back home. If you're just sat around Europa waiting for that to happen, your spacecraft's getting cooked. But if you move on a highly elongated orbit around Jupiter, you spend most of your time on an elongated orbit near the furthest point on that orbit from the thing you're going around. That's when you move slowest. So you can have your spacecraft duck in for a very fast flyby, then fly back out of the radiation belt and spend most of its time safe and not getting cooked while it broadcasts back to Earth. And by doing that, you maximize the amount of time the spacecraft can live to take data and give it back to you so you get the maximum yield from your spacecraft. And the shielding just helps accentuate that. So I think, Fenton, I've ticked off every point you've made there. I apologize that was an epic wall of verbal gibberish from me, but hopefully I've covered everything with a lot of jaunty waffle there.
Yes, indeed. No, well unpacked, I will say. And thanks, Fenton. Hope we covered your questions adequately. We strive for adequacy here at Space Nuts, as you know. And you are listening to a Q&A edition of Space Nuts with Andrew Dunkley and Jonty Horner.
3, 2, 1.
Space Nuts.
Our next question comes from somebody whose name I can't find right at the moment, but it's Kerry from Mount Gambier. As I understand it, light refracts because the speed of light in matter, e.g. glass, is slower than in a vacuum. I also understand that we judge the distance/age of the universe objects by addressing their light redshift. I therefore presume light refraction impacts the redshift. So the question is, do the gas clouds in space slow light down, i.e. impact the redshift? If yes, how is the impact of these dust clouds on the redshift we use for universal distances allowed for in the determining of the age of the universe's objects?
Yes. It's a fabulous question and a really good observation there. So the difference here is going to be that when the light enters that gas cloud, it will slow down a little bit. Now, it's not very much because the density of the gas cloud is incredibly low, so it's a barely perceptible change. But when it leaves again, it will speed back up again. So there's no net impact on the redshift. Essentially, the light coming out of the gas cloud will be at the same wavelength it was when it went in, even though when it was going through the gas cloud, it would have been slowed down a bit. The redshift itself is essentially down to the stretching of the universe. That's kind of how I always envisage it. So the more stretched the light is, the redder it gets. And that is an effect that's independent of the material that it's going through. Now, what you could imagine happening is that, let's say, we were in the middle of a dense gas cloud at the minute, then all of the light reaching us would be very slightly shifted to the red, but it would only be a tiny, tiny, tiny little effect. Whereas the redshifts we're measuring are much more substantive and much more substantial. So you are right that the speed of light changes as it goes through clouds. And in fact, and I'm a little woolly on this, so apologies to any radio astronomers who are listening, but I remember a talk a few years ago that was looking at supernovae and things like that, and talking about getting a feel for the amount of gas clouds on our line of sight to an object, where you had an object that had been lensed, so you had two different images of the same object coming through different paths to us, and seeing the difference in timing of a certain event at radio wavelengths, because one of those paths had gone through more gas clouds than the other, so you have the same pulse arriving at slightly different times because it had moved slower through the gas clouds. So that's where you do get this effect. And I found that talk fascinating, even though I'll quite happily admit a lot of it's lost on me, both in time and distance in the past. Mm-hmm. So it does impact things there, but it doesn't really impact the redshift because when you leave the gas cloud, you speed back up. And also because the degree of change is very, very small.
Okay, there you go. Fairly simple answer to that one. And Kerry, thanks for sending it in. Let's go to our next audio question from Nigel.
Hi, Fred and Andrew. This is Nigel from Brisbane, Australia. I recently heard a report on both Astronomy Daily and yourselves on Space Nuts. It was a story about a newly discovered binary brown dwarf system discovered. I think it was called Gliese 299b. Anyway, binary star systems got me thinking, are they destined to collide? So should we expect the two brown dwarfs to meet and form as one? And the second question is, if they did collide and form one star, would they be big enough in mass to create one star? Okay, thanks for taking my question. Love the show. Keep up the good work. Bye.
Thanks, Nigel. He's just down the road from you, Jonty. You're not far away at all. He probably could have come in and given you that question.
Absolutely.
So lazy of him. So we're talking about a binary brown dwarf system, and will they collide? That was the first part of his question.
So a few little parts to that, and the answer to that is almost certainly no but. And there's always a but. So if you imagine initially that you had those two brown dwarfs orbiting one another, totally separate from the rest of the universe, so nothing else was interfering, then the two would just continue orbiting as they are, essentially forever, because you've got nothing to dissipate energy to slow them down to make them spiral inwards. It gets a bit more complicated, though, in that there are things that can change the orbits to do with the interaction. Now, these all tend to require things to be close together. So if the brown dwarfs are really far apart, that's pretty much the end of the story, unless there's something else in the system whose gravity is perturbing them. But let's say you can bring the objects close enough together, and this isn't just a case for brown dwarfs, incidentally, it works for other things as well. If you have these objects rotating, and they're close enough together, they can tidally interact with one another, and their orbits can change as a result of that tidal interaction. And we've talked about this before with the fact that the moon is moving away from the Earth. The moon has one face pointed towards the Earth all the time, but the Earth is slowly spinning slower and slower, and the moon is moving away as a result. So that's the tidal interaction between the two acting to change the orbit of the moon. Now, because the moon's orbital period is longer than the time it takes the Earth to rotate, that process is acting to cause the moon to move away from the Earth, not towards us. But if you went to Mars, the innermost of Mars's two moons, which is Phobos, is closer to Mars than that co-rotation speed. So Phobos orbits with an orbital period quicker than Mars's spin rate. So the tidal interaction between those is causing Phobos to actually slow down in its orbit, for its orbit to get quicker and quicker and closer, and will eventually cause Phobos to crash into Mars. Well, it'll probably break apart, form a ring, and bits of it will rain down on Mars in 20 to 50 million years in the future. And if I'm having a brain fart and it's actually Deimos that's spiraling inwards, my apologies, but I think Phobos is the closer of the two, and that's the one spiraling in. So you can get these tidal interactions when you're close enough. That can cause the orbit to change, but you'll only move inwards if the orbital period is shorter than the rotation period. If the orbital period is longer than the rotation period, you'll move the other way and you'll move away. The final thing that can happen, well, another way it can happen is you see this for evolved stars. So if a star has a companion and the star gets to the end of its life and swells up to become a red giant, it can get bigger, and then the companion can be moving through the gas in the envelope of that other star, which provides a headwind, and that can cause it to spiral in towards a close encounter as well. Now, sometimes that will just lead to one star numbing up another one and devouring it, and that's all good. But sometimes what that leaves you with is two evolved stars very close together, and that can be, we see it with binary neutron stars, binary white dwarfs, partnerships between black holes and neutron stars, all sorts. In recent years, there have been all these detection of gravitational waves from colliding stars, and they're all from black holes colliding with each other or neutron stars colliding with each other. And that's because those two black holes or the two neutron stars are very massive, but they're also very close together. So there are effects that are explained in general relativity and essentially make my head hurt that cause a loss of energy from the binary as it radiates away gravitational waves. that causes the orbits to spiral inwards. The closer in they get, the more pronounced this effect is. So you get this runaway collapse of the two orbits and they end up hitting each other in a big burst of gravitational waves. I think it's unlikely that'll apply to brown dwarfs, but that's another way they could spiral in. So coming back out from that, in general, if they're quite far apart, there is no risk of them ever colliding. If they're really close together, it's possible. Now, the final bit about could they turn into a star is all about the mass you get. If you have enough mass, then the temperature and pressure in the core will get high enough for hydrogen fusion to start, for hydrogen to turn to helium, and that's when it will really turn on as a star. Now, if you had two very massive brown dwarfs that are each not quite massive enough to be a star, and you add them together, you'd suddenly be massive enough to be a star, and you might be able to cross that threshold. Now, we do see some examples of objects out there that are thought to probably be cases where two stars have merged and form a more massive star that looks out of place. And where this always sits in my mind are these objects called globular clusters. These massive spherical clusters of stars that are incredibly old. They're among the oldest things in the galaxy. And famous examples in our southern sky are things like Omega Centauri, 47 Tucani, things like this. So you've got a spherical ball of stars held together under gravity that is very old. And because those clusters are very old, you don't expect them to have massive blue stars in them, because there's been no star formation recently, and stars that are massive and blue live fast and die young.
Yeah.
So they should be gone. But there's a small group of stars that have been identified called blue stragglers. And they're called stragglers because they should not be there. And for a long time, there was puzzlement as to where these had come from. And I think the currently accepted wisdom is a blue straggler is what you get when you get two smaller, less massive, and therefore longer-lived stars that have merged, forming a more massive star that burns brighter and hotter. So you see what looks like a young hot star that is a product of two older cool stars merging. So you can get things that are stellar size or stellar mass merging with one another to form a star, but it's unlikely to happen with any given set of brown dwarfs.
Okay. Yeah, I get it. Actually, that all made perfect sense. Actually, I saw a story the other day about a young hot star that didn't win any Grammys. So,
Tragic. I need more hydrogen.
yes. Thank you, Nigel. Hopefully, we covered everything with your brown dwarf analogy.
Okay, we checked all four systems and keying with a go.
Space Nuts.
Finally, a text question from Paddy. I'm going to assume this is Paddy the Roof Tyler, but it could be wrong. There could be more than one Paddy listening to us, especially if it's Ireland. But I've got a feeling this is the Australian version. Love the show. Keep up the great work. Since the episode on Mars quakes, I've been thinking about their origins. We know that the orbits of all the planets are slowly expanding, meaning that they are moving away from the sun and they're cooling. Now, given that a molten rock cools, crystals form, and the slower it cools, the larger the crystals, could it be possible that the internal structure of Mars is laced with veins of crystallizing rock that is fracturing, which is the instrument for the quakes? Shortly after the Mars Quakes episode, there were reports of the possibility of water below the surface of Mars. This made me think that perhaps the quakes may be the result of liquid water freezing, thus expanding and fracturing the surrounding rock. This thought of the internal structure of Mars being fractured led me to the question of, is it possible that Mars could break up? And if so, is it possible that this process could be the origin of the asteroid belt when another planet broke up as its orbit drifted further away from the sun? Thank you both, and thank you to Hugh. Cheers, Paddy. He's been thinking a lot about this. I would suspect that Mars breaking up would not be likely due to gravity.
Yeah, gravity wins for Mars for this.
Yes, I figured that. But internal movement, the cooling of the planet perhaps, or the expansion of frozen ice. Interesting theory.
There's a lot of interesting stuff to unpack here. So the effect of an object cooling causing some degree of quakes is actually fairly well established, I think. Now, what needs to be remembered is that most things when they cool actually contract. Water is really unusual in that water ice that's near zero is bigger than the same volume of liquid water at the same temperature. For most materials, they're actually smaller the cooler they get. So what this has led to is on the Moon and on Mercury, there are evidence of very unusual faulting structures, which are thought to be the result of the interior cooling and shrinking, and then you get this cracking of the surface as the surface tries to drop, essentially. And that, of course, leads to quakes. And I believe that quite a number of the quakes that are detected on the Moon are thought to have this kind of origin. You've then got the kind of freeze-thaw processes that we see. Growing up in the UK, the roads there get potholes far worse than we get here in Queensland, even though all the locals on the Facebook groups keep complaining about the potholes here, which always makes me laugh. The reason we get so many potholes up in the UK is because of freeze-thaw. So if you get a very narrow crack and you get water in it, that water then freezes, it becomes ice and it expands, which is unusual. Like I said, water behaves oddly. And that fractures the road, so you get this runaway fracturing of the surface. This, on a different scale, you also see in the degradation of rocks in places like the High Alps, because as rocks heat up and cool down, they expand and contract, and that leads to cracking and fracturing. This is an important process, particularly for my favourite meteor shower, the Geminids. The Geminids have a parent object that is Phaethon, which is often described as a rock comet, and Phaethon has ridiculous temperature ranges through its orbit. When it's nearest the sun, it's about 750 degrees. When it's furthest from the sun, it's 100 degrees below freezing and more. And that's a huge range of temperatures over a couple of years. And one of the explanations for the Geminid meteor shower is that the rocks on Phaethon are persistently being cracked and fractured by this freeze-thaw type process, by the heating and cooling. And then the dust gets kicked off the surface of the asteroid, spreading out into space to give us the debris stream that we get for the meteor shower. So there is a lot to that there. In terms of the quakes on Mars, I think that a lot of them are being linked to, we've got the ones that are linked to impact. So asteroid hits Mars and Mars rings like a bell and you get a Mars quake. You then have ones that we talked about before, which are linked to that kind of residual tectonic energy and the heat movement within Mars. But I think there have been suggestions that some of them are probably also down to the cooling of the interior and that kind of cracking and faulting. So it is a process that would come into play there. However, it's probably not what caused the asteroid belt. So the asteroid belt is often portrayed in kind of science fiction as a planet that was destroyed. And it's probably fairer to describe it as a planet that never got to be. The total mass of the asteroid belt as we see it now is way less than the Moon, but it was more in the past. But Jupiter's the villain here. So when the planets were forming, Jupiter formed quicker because it's a little bit beyond what we call the snow line. So all the water that's out there, and as we said earlier in the podcast, water is one of the most common molecules in the universe. Jupiter was far enough from the sun that water was ice, whereas in the inner solar system it was gas. So suddenly when you've got water ice, you've got a lot more solid material to build planets from. So Jupiter grew really quickly. And as its mass got bigger, its gravitational reach got more impactful and it started stirring up the asteroid belt. That excitation meant that the average orbits of the asteroids were stirred up more. And so instead of the collisions between them being gentle enough to stick together, they entered a range where the collisions are destructive instead. They're colliding hard enough to smash apart. So Jupiter abridged the formation of a planet in that region by stirring things up so much that they couldn't collide and accrete anymore. So the asteroid belt isn't so much a planet that broke up as a planet that never got to form. And that's all thanks to Jupiter doing its thing and stirring everything up. So I think we've covered everything Paddy asked there. I hope we've covered everything Paddy asked there. But yeah, there's a lot of good stuff in there.
I might just add that some of the some of the Mars quakes that have been detected are also being put down to meteorite strikes.
Yes. So they're the asteroids hitting it, make it ring like a bell. And that was part of the reason we put the seismometer on Mars in the first place, was to detect these things.
Yeah. Okay, there you go. Thanks, Paddy. Great question. Good to hear from you. And don't forget, if you've got a question for us for our Q&A episodes, please go to our website and send them in. It's as simple as going to spacenutspodcast.com and clicking on the little AMA thing at the top. And if you want to send us a text question, you can do that, or you can send us an audio question. If you've got a device with a microphone, that's all you need. And don't forget to tell us who you are and where you're from. Jonty, thank you so much for answering all of those questions. I'm going to make you do it again next week.
It's always a pleasure. It's good fun. Thank you for having me.
Thank you, Jonty. Professor Jonty Horner from the University of Southern Queensland. And look, Hugh in the studio was a no-show again today. Now, a lot of people ask us if Hugh is real. I'm starting to think you might be right, that he doesn't exist.
Yeah.
And from me, Andrew Dunkley, thanks for your company. Catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.